ask you. So, okay. While that's coming up, let me go over what the rest of the term's going to be like and what we've got going on with that. All right, number one. I already said about student course evaluations. You know about those, right? Okay. Number two, today we have class until about 5:30, 5:25, and then I'll be in the office until around 6. Okay? I've gotten everything graded that's been turned in up till today, but I've received this many papers today. Today, okay? And so I was hoping over the weekend to get your grades in Blackboard. I didn't get them there. It turned out being a way busier weekend than I had thought it would be. I did quite a bit of work outside and got eaten up by fire ants and chiggers, okay? And both of those are very miserable to try to sleep or and even getting anything done. I'm just sitting itching all the time. So and then too, we had company most of the weekend, and it was a family of our godson. So they're close friends of ours. And what I didn't know was that he was going to bring with him, he's an upcoming junior in high school, and he's taking AP Calculus in high school, and he was given a packet of about 63 to 65 questions to have done before the school year began. He had most of them done, but there were a few that he had trouble with, so we worked quite a while on Saturday night and quite a while yesterday afternoon and evening finishing. I was helping him with that because he hasn't had the course right immediately to that. He's going straight from pre-calculus to the AP Calculus, and he was supposed to have something in between, and he's skipping that something, so I was having to help him do that, and that was the time I was hoping to be entering grades on Blackboard, and I just didn't get to do so. So I've got this much additional grading to do today, but as soon as I can get my head above water with this grading, then I'll be putting them out on Blackboard. So that 30 minutes a day, I won't be there yet. I'll guarantee you that. Now, number two, tomorrow my office hours are 8 to 8:30 here on this campus, and then I'm in class from 8:30 until 10:45. That'll be the last class for that one. Then I'm in my office again from 10:45, and tomorrow only till around 2 or 2:15, because I have an eye appointment across the street here at the UAB West. They moved it to 2:30. They had originally said 2 o'clock, which was fine with me, because last time I sat and waited about 2 hours before I saw someone. I had time to get to the Birmingham East Campus for my last class. Tomorrow, with it 2:30, if they go until 4:30, I'm in trouble because I've just barely got time to get to the other campus. So we'll see what happens with that. But I'll be in my office until around 2 or 2:15. Then I'll go over for my appointment. Hopefully it won't take as long. All right, then I'll be on the Birmingham East Campus, and that's in the Ethel Hall building, which is Health Professions Building, room 214. I'll be there from teaching a class from 5 to 6:30, and I'm usually there a little before 5 if I can get out of the eye appointment in time, and until I usually stay usually close to a half hour after class is over with in case there's questions and stuff like that. So you can catch me then. So that's Tuesday. Those are the last 2 days of class. Monday, Wednesday class is the last day. Today, the day you've been dreading all term is here, last day of class. Okay? And then tomorrow will be the last day of class for Tuesday, Thursday. Then on Wednesday, no classes, all day, people turning in stuff for the finals. So I'll be down in my office from 8 in the morning until 6 in the evening on this campus, 8 till 6, all day long. This is all day Wednesday, right? Okay. I don't have any other campus to go to, no other appointments, nothing else, be down there. That's when I hope to be getting, if I don't get time tomorrow, hope to then get everything in Blackboard. Okay. Now, you know where my office is. Room 265, yeah. Down at the end of the hall, just before you hit the wall on the last door on the left. 265. Down that half flight of stairs and all the way to the end. Okay. So that's Wednesday. Thursday, oh wait, no, I just remembered this. Yeah. Wednesday, they called a meeting for 1 o'clock. So I'll be on the Birmingham West Campus from 1 to, I'll have to leave here at 12:30. I forgot that. I haven't told my other classes that. I'll be there, I'll leave here at about 1:30. And I'll be in the meeting 12:30. Leave here at 12:30. So I may not get everything put on Blackboard because of this. But then I'll be over there. The meeting, this is a meeting that goes usually a long time, so I'm guessing 1 to 3. But then whenever the meeting's over with, whenever that is, I'll go back to the Birmingham West Campus. I mean, I'll still be there, but I'll go to my office in room B122. That's Dr. Pruitt's office. I'll be in the copy room behind the secretary's desk. I'll be there from whenever the meeting's over until around 6. I won't be driving back here, then just turn around and drive home. So I'll be there. I'm hoping 3 to 6, maybe a little longer. So that's Wednesday. I forgot about that in my first 2 classes. Okay, Thursday. Okay, all day long here, I'll be from 8 o'clock in the morning until around 4. At 4, I've got to leave because I've got to pick up something for that last class, and I'll be heading to the Birmingham campus, Birmingham East campus, I'll get there hopefully a little before 5, and I'll be there through 6:30. Now, there's no class that day, so you can come anytime during that time and turn in any work you want to turn in. Now, this is something I forgot last week. I also forgot for my first class this week. Friday is a duty day again because we have Fridays off June and July, but this coming Friday is August. Okay? So I will be on campus here on this campus from 8 till 12. None past 12. If stuff isn't in by 12 o'clock on Friday, it's going to be an incomplete because I'm hoping to take Monday off and not be back. So try to get everything in by Friday at 12 noon. Don't wait till 12 noon because I'm leaving at 12 noon, so plan to anyway. All right, any questions on how things are going to pan out? Please do the student course evaluations before August the 8th, but I'm not going to be around August 8th to remind you, so get them done before, just so we'll be finished with that. Okay, I'm itching all over. I can't help it, sorry. Okay, now, where we left off last time, or at least my mark in the book, was in Chapter 14, Multiple Integration, and it was Section 14.6, Triple Integrals and Applications. We're into the application part of that, and the first of these applications or the next application is center of mass and moments of inertia, and for some reason, it's not opening. There, it may be coming. There it is. Center of mass and moments of inertia. Is this where y'all had us leaving last time? Because I think we were working on example 4, ran out of time, but I think you had opportunity to get that done. Okay. Now, this to me, now both of you are pre-engineers? Okay, which kind? Electrical? Second? Civil? Okay. Maybe in your statics and dynamics classes, you might run into this. I imagine you will run into some of it. But they may teach it with slightly different terminology and stuff, so I don't want to focus too much on this. And basically, let's just go through this part pretty quickly, because the next part, well, actually, just about everything else for the rest of the time here is going to be pretty much a PowerPoint show, okay? Because I'm not planning to test you. Let me again look, y'all have your test in front of you there. Let me go back and check again. The volume of a solid was what we were doing before this, wasn't it? Yeah. So basically, we have covered all the material that's going to be, that is on your final exam, okay? So the rest of this is basically going to be slideshow type stuff, and just in case you need it in the future, you will have been exposed to it, okay? So let's start with this one, center of mass and moments of inertia. Now, if this sounds sort of familiar, it should be, okay, because we've done center of mass, if not in this class, in a previous calculus class. Consider a solid region, Q, okay, somewhere in space, solid region Q, whose density is given by the density function rho. Okay, now that looks like a P, but it's a rho. Now that function could be a constant function. If so, that's pretty easy to deal with. Or it could be a function that varies from spatial locations. Now, the center of mass of a solid region Q, that solid region Q, if you know its mass M, is given by, the center of mass is x bar, y bar, z bar. Okay? Now, the mass, given mass, is the triple integral over that whole region Q, however that breaks out, of your density times the volume. Because if you think about what density is, it's mass per unit volume. So volume times density should give you mass. Here's the density, there's the volume, or the dV, and summing those up on the triple integrals, that would be the mass of the solid. Now that's the mass of the solid. It has no, it doesn't vary on depending on which center of mass coordinate you look at. That's the mass of the solid. Now, these two things are called the first moment, and there's going to be one on the next page too, the first moment in about the xy plane. Okay, now what does that mean? I'm sorry, xz plane. I can't read. YZ plane, okay. So if this is the YZ plane right here, the first moment with respect to this will be the distance you are from x, from this YZ plane, the perpendicular distance from the YZ plane, that would be your x coordinate, times your density function, times your dV. Again, a triple integral over the whole region Q. So you see the only thing you've got different between the moment, the first moment about the YZ plane, is, and the mass, is the x coordinate. Okay? So your and then when you take this, I'm jumping ahead, and divide by that, that gives you your x bar. Okay? Then the moment about the xz plane, there's the xz plane over here. Y value is how far you are perpendicularly, the y value from the xz plane. Then that would be the triple integral of y times the density function times the volume increment. And divide that by the mass, and that gives you y bar. Right? And I bet you can tell me what the moment about the xy plane would be. What you reckon? There's the xy plane, is the floor down here, and the perpendicular distance from that is z, exactly. So that would be the triple integral over the solid region Q of z times the density function times your volume increment. And that then divided by the mass again, that would give you your z bar. So that's how you get the center of mass of these three. There's the third one. the moment about from the xy plane would be the triple integral of z rho dv. Now, and just like I said before, the x bar would be the moment about yz, the one that doesn't have the x in it, because its integral would have x in it. And then the rest of the integral looks very much like the mass integral. So think of it that way. Divide that by the mass, and you get the center of mass x coordinate, divide the one with the z in it, with the y in it here. That's the moment about the xz axis plane divided by mass, and z bar would be the moment about this one, which would be z times that quantity. The quantities m, yz, m sub xz, and m sub xy are called the first moments of the region Q about the xy, xz, and I can't read, yz, xz, and xy planes. Okay? The first moment for a solid region are taken about the plane. The first moments for the solid region taken about a plane, whereas the second moments for solids are taken about a line. For first solids, first moments about the plane, second moments, that's going to be, say, an xy, second moment, about the line that would be a z. So let's see what that is. The second moments are moments of inertia about the x, y, and z axes. X-axis here, y-axis here, z-axis there. Okay? Then that would be a function of, about the x-axis, function of y and z, which would be, here's Davis. You know, I didn't mark forward, did I? Okay. Ricky was here earlier. Got it, thank you. Evan's here and Jasmine's here. All right. Now, before you leave today, be sure you pick up your first and second test. Can't return research papers to you, but first and second test, and also get your third test. I had it made out. I didn't realize I was completely through with it. I could have had it run off Wednesday if I thought I still had some more typing to do. I guess I just had more time than I realized and had actually finished it. Okay, so the moment of inertia, which is called the second moment, and these are about lines, x, y, and z axes, that would be, and if you think about it, y squared plus z squared would basically be kind of like a circle around the x-axis, right? And x squared plus z squared would be a circle around the y-axis. And x squared plus y squared would be a circle around the z-axis. Okay? So you take those circle-looking elements here, y squared plus z squared times the density function times the volume increment, and when you divide this by the mass, that gives you the center of moment of inertia about the x-axis, about the y-axis, and about the z-axis. So notice this one doesn't have the x in it. It's y squared plus z squared. This doesn't have y in it. It's x squared plus z squared. This doesn't have z in it. It's x squared plus y squared. So all the rest of it looks the same, and that part here looks a lot like the mass. So when you divide by mass, you're going to, these are the moments, okay? And for problems requiring the calculation of all three moments, considerable effort can be saved by applying the additive property of triple integrals and writing this, okay? This is the moment of inertia. This isn't quite right. Okay, here we are. moment of inertia from the xy plane, which would be z squared. See, inertia is the distance squared, the center of mass, and moment, first moment, would just be a distance. So that would be, this would be a lot like your moment, your first moment with respect to xy would be z rho dv. The second moment of inertia would be z squared rho dv. And the moment of inertia with respect to the xz axis would be y squared rho dz. And with respect to the z axis, xy plane, I'm sorry. It's xy plane, xz plane, and yz plane. That would be x squared. Okay. Now, if you have those, and they suggest this will be easier, this one plus this one yields your I sub x. Because if you think about it, these two would then be x squared plus y squared, so that would be your I sub z. That would be your I sub z. I'm sorry, I said I sub x. No, I sub x is fine, because that would be go back. No, I think they have these wrong. These two added together, because this is the same, that's the same, that's the same. X squared plus y squared. That's this one and this one. And they're saying that's I sub x, but x squared plus y squared would be I sub z. So I think they just got that wrong. Yeah, that's I sub z. That's supposed to be a z. This one is y, that's correct. Let's see. I swear, I think this isn't really making a lot of sense here. This one right here, that's, oh, okay. I was pointing to the wrong one. This one plus this one, no. This one plus this one. Yeah, I was pointing. The top two here make this one, and that's correct. Z squared plus y squared, okay. Not seeing well, okay. And then the y would be this one and this one, because x squared plus z squared would be y, okay. And then the z would be x squared plus I sub x z plus I sub y z, and that would give you I sub z. Okay, sorry. So probably easier to evaluate these first and then add the appropriate two together. Because you don't have to go back and recalculate. You're using this one here and you'll use this one over there too. That's going to be the same. So just calculate these three and then you get those three by adding them in different ways. And the whole calculation will be easier. All right, so let's see. Are we going to do example 5? Why not? Finding the center of mass of a solid region. Find the center of mass of a unit cube. And when it says unit, that means each of the dimensions is 1. 1 in the x direction, 1 in the y direction, 1 in the z direction. So it's a cube of volume 1. Okay, 1 cubic unit, whatever they are. And so that's a unit cube. Shown in that figure, given by that the density at the point xyz is proportional to the square of the distance from the origin. okay? Of any point x, y, z, the density at any point x, y, z is proportional to the square of its density from the origin, which is a little bizarre because that tells you at the origin there's no density. So you have a little hole there at the origin, and then it's very low density near the origin and getting greater and greater density as you go out. The greatest density would be this corner right up here. These corners here, this one, that one, would be a little bit less than this, but still there, and then these points here would be a little bit less than these would, and then the closer you get to the origin, the lower and lower the density would be. So this statement here, given that the density at a point x, y, z is proportional to the square of the distance from the origin, so here's some point x, y, z here. This probably is an interior point. Looks like it's fairly close to the this plane here, maybe right on the plane. It's hard to tell, but when it says proportional to, so rho of x, y, z is proportional to, and I'll show you these symbols, the way they usually refer to them. Okay, so the density, rho, is a function of x, y, and z, is proportional to, that's the symbol for it, is proportional to, the square of the distance from the origin, so that would be x squared plus y squared plus z squared, okay? And to make that an equation, I wrote a p. I just said don't write p, write rho, and I wrote a p. Okay, rho as a function of x, y, and z is equal to some proportionality constant times x squared plus y squared plus z squared. Okay, and that's where they get this statement down here. Is proportional to can be changed to is equal to by putting a proportionality constant. That's what they get here. Okay, now, because the density of x, y, z is proportional to the square of the density between 0, 0, 0 and x, y, z, that's not a very good sentence or clause there, you have rho of x, y, z is equal to k times x squared plus y squared plus z squared, where k is the constant of proportionality, whatever that is. You can use the density function to find the mass of the cube. And if you remember the mass, its formula was the triple integral over the cube of rho of x, y, z dv. Okay. Now, remember this. This is a simple shape, and your dv is merely going to be dx, dy, dz in any order you want them to be. Because this is a simple one, you'll be going, that's supposed to be a z there, it looks like an x. I don't know what's going on. It goes from 0 to 1 here, 0 to 1 there, and 0 to 1 there. Okay? And the density function is your k, so bring that out, the proportionality constant, 0 to 1, 0 to 1, 0 to 1, and this will be x squared plus y squared plus z squared dx, dy, dz. Okay? Now, that is not going to be a very difficult integral to perform, so how would you say we did it? Now, just randomly put down x, y, z in that order. You can do it in any order you want to, but what would be the antiderivative of that if you were integrating this? Don't have much room. I'm going to come up here and write that one. What would that be? First, do your integration with the dx. Well, the k is going to be out there. That's your proportionality constant. This last one are your z's, 0 to 1. This is your y from 0 to 1. What is the antiderivative of this with respect to x? Can anyone do it? can't hear a little louder. To respect to x. That's just the one I wrote down first. It really doesn't matter which one you do first. Did you say x cubed over 3? Yeah, perfect. X cubed over 3 plus y squared x, because that's just counted as a constant, plus z squared x, right? And then you evaluate that from 0 to 1. Now these are the values for x. X equals 0 to x equal 1. Okay, so that's what we do next, is k times integral from 0 to 1 times 0 integral from 0 to 1. And let's evaluate that when x equal 1. What's the first value? Help me. 1/3 plus, it's, just y squared, right? Plus z squared, second, plus z squared, perfect. And then when you plug in zeros for the x, all goes to 0. So now we do this next with respect to y and respect to z, okay? And don't forget your k, it's out there. Integral from 0 to 1, that'll be the dy that we do, dz that we do last, 0 to 1. So let's do the antiderivative with respect to y. What would that be? Did you say, what, say again? 1/3 y over 3, plus y cubed over 3. No. With respect to y, z is just a constant, z squared y. Right? Evaluated from 0 to 1. Remember, these are values for y now, because you're doing the y second. And then ultimately you'll do the dz in a little bit. So this will be k, don't forget it's there, integral from 0 to 1 of, and what does this turn out being? 1/3. I'm sorry.
Is it easy?
Okay, no, we're plugging these values in for your y's.
1/3 plus
1/3 again, plus z squared, right? Because y is 1. You plug in the zeros and everything goes to 0, so that'll be dz. Okay, one more integral to go. This will be k, and this will be what? 1/3 z plus 1/3 z plus z cubed over 3, and that's evaluated from 0 to 1. Okay? All right. So what will that yield us? K times 1/3 plus 1/3 plus 1/3, and that would be negative k. I can't write. Yeah. Something doesn't quite seem right about that, so let me, well, I said negative k and wrote down k. Negative k. Oh, It's not a negative. It is a K. There's an equal sign in front of that. Duh. Okay. So that's equal to K. Your density, constant proportionality, and everything's they did things in the reverse order for us. They did their integration a little bit differently and stuff, but still comes out exactly the same mass is K. Your constant proportionality. Okay. Now, it says find the center of mass of the unit cube given that the density is proportional to the square of the distance from the origin. Okay. All right, we got the mass. Okay, it's asking for the center of mass. Now, oh yeah, okay. So we're looking for first moments. And I tell you what I'm going to do. I'm going to erase everything except for, I'll write back down what the total mass is, because we shouldn't have to do that on our own. Okay, so let's write it up here. The mass is equal to K. My head feels like it's clogging up. I had a sneezing fit in my last class, and it just got all the juices flowing. And I don't know how that happened, but this thing fell out. So I'm going to have to put that back in, and hopefully it won't mess up anything. All right. So let's move on. So, what we're going to deal with now is first moments. Now, the first moment, remember, was M, and doesn't matter which one you do. Let's do YZ, because that's the moment with respect to the XY. That's a Y there. I can't read my own writing. Let me see if I can clean this up some. Oh, the wrong thing cleaned up. Okay. YZ. So this is going to lead to your X bar, the X component of the center of mass. Okay, so what will this be? All right. Your density function is still the same as it was. So this is a triple integral over the region, and that's going to be 0 to 1, 0 to 1, and 0 to 1. Okay. Now my 1s seem to run into my integral signs too much, so I'm going to see if I can. Don't know why that came back on. Yeah, okay. No, I'm going to be able to breathe one of these days, but right now it's hard. Okay, what's that moment? This is with regard to the YZ plane. So this is going to be X times the rho, and the rho was this, so I'm going to bring that constant out front again. And the rest of rho is X squared plus Y squared plus Z squared. That will be the X part. Okay, and again, I want to say it doesn't matter what order you do. And it really doesn't. It just depends on which ones you want to go first. I'm thinking, because of the way we've set it up, that we probably won't. No, I don't think it really matters. Let's just do dx, dy, and dz again. The book, I'm sure, is going to do a different order, but this doesn't matter because all three of them are equivalent. What does make a little bit of difference is the fact you got more x's here. So you want to do that first to get rid of them, keep them from getting so big, or do you want to do it later? Seems like to me it makes sense to do it first. Keep them from getting any bigger, because you want to hang on to your y's and z's until you get near the end. So let's do that, okay? Do I need to multiply that through, or can you do the integration without that? You tell me. Which would be easier?
Yeah.
Multiply it through? Okay, this will be k times the triple integral, 0 to 1, 0 to 1, and 0 to 1 of x cubed plus xy squared plus xz squared. Okay? Dx, dy, dz. Okay, let's do the innermost integral first, which is your, with respect to x. Okay? So that would be k times the integral from 0 to 1. My pen drug like crazy there. Goodness, I can't get this to right. And the one of the other, doesn't matter which, 0 to 1. Let's do the antiderivative of those first. X to the fourth over 4 I can't hear. Isn't it x squared y squared over 4? Wait. Goodness gracious, I say 4. That's a 2. X squared y squared over 2. My pen is dragging like crazy. Okay. And then z. Goodness gracious. Okay. What would be the third integral? Z squared. The pen is just not writing. Okay, let me try it again. X squared y squared over 2. All right. And then this would be dy dz. Okay. Sorry, my pen is just, I move it across the thing and nothing happens, or it leaves stray marks, or it bops along between 2 points. I don't know. I hope the system isn't going bad. Okay. And we're evaluating that one from 0 to 1. X equals 0 to x equal 1. I like to write that down because that's what I took regard to, and that way I don't plug into the wrong thing. So what will this one be? K is out front, and you've still got a 0, 1 to go on Z and a 0, 1 to go on Y. So what's your X here? Anybody? You're going from x equals 0 to x equals 1. So let's do the upper x first. What would that be? 1/4. Y squared over 2 plus z squared over 2. Okay? And this goes from, well, we've already evaluated it. Sorry. That should have been a parentheses there. dy dz. Okay. Let me pause a moment here. Find my tab. And Rachel's here. All right. Okay, where we are, we're doing example 5 on page 1019. This is in chapter 14, multiple integration, section 14.6, which is all right. Let's do our dy next. So this is equal to k. I hope you see already the k's are going to cancel out because k is just a, oh, I was just going to say, chapter 14, multiple integration, section 14.6, triple integrals and applications, and we're on example 5. And this one's also, you can go to larsoncalculus.com for an interactive version of this type of example, and we're doing this one. Oh, okay. I was going to say that doesn't look like what we've got going here. Okay. Now, a little the opposite of what we're doing. They saved the x to do last. We did it first. It's not going to matter. The order here does not matter. Or at least I hope it doesn't. We're going to see. Okay, now we're going to do the integral from 0 to 1. And we're going to do the next one, but this time we're doing dy. That's how I wrote it down. So what would that be? Anybody? Integrating this thing here with respect to y. 1/4 y plus y cubed over okay. Goodness, that drug again. Okay. What did you say?
Over 6, 2 times 3.
Yeah, because it's over 2 there, and yeah. Y squared over 6, I mean y cubed over 6, my nose is itching, and the next one would be plus partial of this, I mean, and say again? I can't hear.
I didn't say anything.
Yz squared over 2, right? Because the constant z squared over 2 stays the same. Okay, and this is evaluated between 0 and 1. And then you have your last z dz at the end here. Whew. Okay. So let's do, and remember these are y values, y equal 1 to y equals 0. Okay, so this will be k times the integral 0 to 1. And what would that be? 1/4 plus 1/6 plus 1 getting lost where I am now. That would be just your z squared over 2. Right? Right? Okay. And this, we're going, the last one would be dz. Okay. Whew. Okay. Now let's go on and combine 1/2 and 1/6. What do those add to? Least common denominator of 12 be 3/12 plus 2/12 is 5/12. So I really, let's just write it here. I was going to, because it doesn't take that much. 0 to 1 of 5/12 plus z squared over 2 dz. All right, now what does that give us? K times okay, yeah, you probably said it right, I just can't hear. 5/12 z, perfect, plus, second, over 6, perfect, evaluated from 0 to 1. Okay, there's another stray mark. Okay. And what would that be? K times 5/12 plus 1/6, which is 2/12, and this would be 7/12. K. Okay. Yes. Okay. Now, we can go through this entire process for each one, and they're all going to come out 7/12 K, because the variation with your density, your distances, everything are equal. So this would be your m sub yz, but it will also be your m sub xy, and it'll also be the m sub xz. Okay. By that, and then it's a pretty simple process to do your x bar, since this is the one with the x in it. Boy, in the end of my last class, my voice just started going on me. I drank some stuff during between the classes. I got it back, but it's going fast again. Okay. Your x bar is your m sub yz divided by mass, and your m sub yz we just found out to be 7/12 K divided by K. So we wind up with just 7/12. Okay. Okay. I'll just write 7/12. I was just going to leave it there, but since these marks are scattering all over the page, let me get them out of there. Too much. All right. So the X bar will be 7/12, and I think you see the others, since everything is equivalent, this will also be Y bar, and that'll also be Z bar, as opposed to Z bar. Okay? So your center of mass will be at the point 7/12, 7/12, 7/12. Okay. Now, what does that tell you? I would have almost guessed it would be a little bit more than that, but it's more than halfway, because 6/12 would be halfway. But you see the density is getting greater the further you are away, so you figure the center of mass would be further from the origin than it would be anywhere else. And sure enough, this does give you the value of where that would be. So, goodness gracious, dizzy with the clogged up head. So let's just say we're going to let each of these blocks represent 1/12 of a unit. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this would be where 12/12 would be. So 12, 11, 10, 9, 8, 7. So it would be this one in this direction, the same 7 in that direction. 1, 2, 3, 4, 5, 6, 7. So it would be that block right there, and then 7 up, wherever that would be here. So this would be the place. Now the total distance is 12, 12, and 12. So you're up near this corner where it is the densest. But you still got a ways to go. Okay? I'm a little surprised it's that close to the center. I would have thought with the density function being like it was, it would have been closer to the corner. It is closer to the corner, but not by as much as I would have expected. So let's see how they did it. They did it slightly differently than what I did. So let me clear this if y'all okay with that. Okay. You can use the density function to find the mass of the cube, which we did, and the symmetry of the region. Any order of integration will produce an integral of comparable difficulty. So they're all going to be the same. They seem to like to do dz, dy, dx. It doesn't really matter, okay? And by doing that, and the k, of course, is a constant, so it can come all the way out. And then you do that, and you have, and this is just like we did it. Now, they are combining the two constant ones. If you're doing dz first, x squared plus y squared is a constant. That's times z. And then that would just be z cubed into 3. And when you evaluate, and those are values for z there, remember you can see, then this would be x squared plus y squared plus 1/3. Same thing we get, we just did it the x first, okay? Then do it again, and you get x squared plus 1/3. These two are still, okay, no, you're doing dy now. Okay, I see what they've done. A little bizarre, but since it's dy, they put the dy at the end and move the 1/3 here. So it's x squared plus 1/3 times y, and then y cubed over 3. This one right here, they put down here, and they evaluate that 0 to 1, and that would give them, and those are values for y, so this would be x squared plus 1/3 from here and 1/3 from there. So that gives you x squared plus 2/3. So they did theirs a little differently. But you see it comes out exactly the same. This would be x cubed plus 2/3 x. And when you evaluate that from 1 to 0, that gives you 1/3 plus 2/3 is 1 times k, which is just k. Okay, there's your mass. Surprisingly a little bit, but true. So the first moment about the YZ plane. So that would be the X distance out from the YZ plane. This is your YZ plane right here. That would be, the distance out would be X. So that would be K, again, from your density function. This is K, it comes out front. And the integral, and they're doing the dx last, which is fine. There's no reason not to. We did it first. It doesn't really matter. But all these are 0 to 1. That's why it really doesn't matter too much. But what you'll see they do next is sort of interesting. Since they're doing their first with respect to z, that's not going to influence the x any. So they bring the x all the way from here to this last integral, which is your dx, because you're not doing anything with it, okay? It's just carried along there. So, frankly, that was sort of an extra step to write in, and it didn't gain you much, but it did gain you a little bit. Then you do the first one here, the innermost one with respect to z, you'd have x squared plus y squared times z plus z cubed over 3, which is what they do now. The x can be factored out of the two inner integrals because you're not going to do it until the very end, because it's a constant with respect to both y and z. You don't have to do it that way, but you certainly could. After factoring, the two inner integrals are the same for the mass m. That is exactly what we... Okay, sorry. Yeah, this is the same for the mass m. It's exactly what we did before, and you can just go back and reproduce those two integrals. Therefore, you have the first moment with respect to the YZ plane would be k on the outside, and then the integral from 0 to 1 of x times x squared plus 2/3. If you go back and check, that's what we got from those first two, and then the dx. And this, that's multiplied through, and that would be k times x fourth over 4 plus 2/3. Okay, so it's 2/3 times x. So it's x squared over 2, so the 2's go out, so it'd be x squared over 3. So that's how they get this one. And then evaluate that 0 to 1, and this would be k times 1/4 plus 1/3. And least common denominator again, 12. That would be 3/12 plus 4/12, 7/12. Exactly what we got before. Okay? So 7/12 k over 4. It's a moment with respect to the YZ plane, how the distance from it. Then take that, divide it by the mass. It's the moment with respect to the YZ plane divided by the mass. That's your x bar. This was 7/12 k divided by k, if you remember back that far, and that just gives you 7/12. But because everything is symmetric, from the nature of the row, symmetry of x, y, and z in the solid region, you have the x bar plus y bar plus z bar. X bar is equal to y bar is equal to z bar. Center of mass would be 7/12, 7/12, 7/12. And that's all they showed. And that was a very simple center of mass. The next example, 6, is a moment of inertia. They're not showing it in the slide set, and it's not that bad of a problem, but since they didn't show it on the slide set, we've already covered, didn't I just say we have covered everything we need for your test? So let's just do the slideshow, and since it ends here, we'll end there. Now, let's discard this and go to the next section. And because my computer froze up on me earlier, I'm having to recreate all this. So this goes to 14.7, I think it is. And by the way, homework exercise there for 14.6, especially do the odds 3 through 9. They're all at Calc Chat, 3's at Calc View. Do 11, it's at Calc Chat. 13 through 17 are just setting up a triple integral. You don't actually have to evaluate them, but those should all be at Calc Chat. And then the volume exercise, this one for sure do any of the odds 19 to 23. They're all at Calc Chat. 19's at Calc View. They have you rewriting the order of integration. You can do any of those you'd like. 25 to 29, they're all at Calc Chat. 25's at Calc View. And 31 and 33 are sort of the same type problems. They're all at Calc Chat. 35's the same kind of problem. It's at Calc Chat. And then the center of mass, that'll be up to you whether you want to do that one, 37 or 39. They're both at Calc Chat. 37's at Calc View. 41's the center of mass. It should be at Calc Chat. And then you can do any of the others that you're interested in. Okay. So let's leave that and go to 14.7. And I've been scrolling down, but I stopped to, all right, 14.7. We're almost through with chapter 14. Don't think we're going to get to 15. If we do, it'll just be PowerPoint show. And we're still multiple integration. And let's go to the slideshow from current slide. All right. Chapter 14, multiple integration. 14.7 is triple integrals and other coordinates. Now, I don't know if y'all are going to need these. I forgot to mark. Yeah, I marked right through when she came in. Yeah. If you'll need these, I didn't catch your major, Davis. What?
Meteorology.
Meteorology, okay. And now, actually, you might do some different things because you're basically going to be modeling the atmosphere, which will be far better done probably in spherical coordinates. Whether you do any of that or not, I don't know. But if you were to model, that would be it. And Rachel, what was your major? Civil engineer. So two of you are civil and one electrical and one meteorology. Okay. So this is other coordinates. Okay. You could have slid that under my door. Okay. Okay. No problem. All right. Now, our objectives in this section is write and evaluate triple integrals in cylindrical coordinates, and we'll write and evaluate triple integrals in spherical coordinates. Now, I think we'll just go a slideshow of this. If you ever need it, then certainly you can go back and retrace it. Now, we're pretty close to the point where we normally do take a break. And since we're starting a new section, do you want to take one there or want to just keep trucking? Huh? Break? Okay. So let's just pause it here. All right. Just going over one more time when things are, how the term is ending up. Okay? Now, this class, we may not go fully till 5:25, but whenever we end, I'll be in the office until 6, okay, today. Tomorrow is my last day of class for Tuesday, Thursday classes, so they will be in the office from 8 to 8:30, then in class from 8:30 till 10:45, that's on this campus. And then, unfortunately, tomorrow I have an eye appointment at 2:30 right across the street here. So I only have office hours from 10:45 until about 2 to 2:15, and I'll head across there to my eye appointment. And last time I thought it was going to be pretty quick. I sat and waited for about 2 hours. Okay, so this time I'm going to figure it's going to be about 2 hours. Hopefully they'll get through with me sooner than that. But anyway, that goes about the time I get out of there, I'll probably have to head pretty quickly over to the Birmingham East Campus for my physics class, and that goes from 5 until 6:30. So I'll be over there, and that's in the East Campus, Ethel Hall Health Professions Building, and I'm up in the second floor in 214. Okay, so that's tomorrow. Wednesday, I'm back here on this campus, and no classes, so I'll be in the office from 8, unfortunately only until about 12:30, because they called a meeting for a committee I'm on, and that's at 1 o'clock over on the Birmingham West Campus, so I'll be over there. The meeting starts at 1, and the others I've been to of this nature have gone about 2 hours, so I'm going to be in the meeting from about 1 till 3, hopefully get out sooner than that, but once it's over, then I'll go to my office over there, which is in B122. That's Dr. Pruitt's office on the West Campus, and I'm behind the secretary's desk in the copy room. So that's where I'll be, I'm guessing from about 3 to 6, okay? So I'll be over there then. That's tomorrow. Thursday, I'll be on this campus from 8 until close to 4. No, yeah, that's right, close to 4. And then at 4, I've got to start getting my stuff together to head back over to my last class over there when they turn in their finals. And I'll be there on the East Campus again in the nursing building, Ethel Hall building, from 5 to 6:30. And I'm not going to be there much after 6:30 because they're just turning in their finals. And so we'll be there, but I will be there until 6:30. Now, then on Friday, I was telling before that Thursday is when I have to have papers in. I realized Friday is a work day this week, so I will be here on this campus. Wait, no, which campus will I be on? On Friday, so I'm usually on the Birmingham campus, so I'll be over there from 8 to 12. So Birmingham campus, 8 to 12. So if we're running that late, be sure you turn it in there. I won't be coming back to this campus, so I won't find anything that's under my door or anything else if it's got put there after 4 o'clock on Thursday. Not at all. So you're going to get an incomplete. So on Friday, take it to the Birmingham West Campus, again, B122. That's in the academic building, B122. And that's where I'll be 8 to 12. Not going to be there much past 12. 8 to 12, I'm out of here. I'm not planning to come in on Monday. I'm going to try to take a vacation day that day. Not vacation, personal leave that day. And will then be not back until fall term. So if you don't have things in on this campus by 4 o'clock on Thursday, on the Birmingham East Campus by 6:30 on Thursday, or Birmingham West Campus by 12 o'clock Friday, it's an incomplete. Okay, so try to get them in by then. Okay? All right, and please do the pseudo-course evaluations. Okay, any questions on how to do the pseudo-course evaluations? Check your email. You'll find, I think it's just from something like Lawson Coordinator or something like that. You find that email, it says pseudo-course surveys or something like that. Click on that, has a link to go to. It's real easy to get there. Yeah.
I know you just explained what time you're going to be where, but say Thursday again, what time?
Okay, Thursday, I'm here from 8 in the morning until 4 in the afternoon. At 4, I have to leave to go over to the Birmingham East Campus. I'll be there in Ethel Hall building, Health Professions building, from 5 until 6:30. Okay, and then I'll be leaving shortly after 6:30, and then on Friday I'll be on the Birmingham West Campus in B122, just like I will Wednesday afternoon. Wednesday afternoon from 3 to 6, or approximately 3 to 6, and Friday morning from 8 to 12. Okay.
And your office is where again?
I'm sorry?
Where's your office again?
On this campus?
Yes.
Okay. Let me show you on the map. Okay. You're right here. You go out the door here and hang a left. You go down that little half flight of stairs there, past the restroom. So all the way down, not to the end of the hall, the last office on the left is 265. Okay. Sorry, that took way longer than I thought it would. Okay. So, I think we went over the objectives here. So let's move to triple integrals and cylindrical coordinates. And by the way, there's a person featured in this section, Pierre Simon de Laplace, a French mathematician. He has been called the Newton of France, pretty impressive term. Published many important works on mechanics, differential equations, probability. Looking at his dates there and seeing how he's dressed, I would not be surprised if he didn't participate in some of the French Revolutionary activity, because it looks like he's got on some sort of military getup. I know several other French mathematicians. And France was sort of head of the game in many things. They weren't head in calculus, but they were in many other aspects. And so I wouldn't be surprised if he wasn't either French Revolution or Napoleonic or something like that. They don't say anything here, but pretty interesting character. There are things called Laplace transforms. There are the Laplacian. So there's several things in both physics and math that you run into. So, triple integrals and cylindrical coordinates. All right. When you're dealing with rectangular conversion equations for cylindrical, here's your cylindrical coordinates. Think of your polar coordinates in 2 dimensions. In polar coordinates, you have r and theta. Okay? So a little section here in the plane here would be an r, dr, d theta. That would be this section here, because r would be how far out you are, and then r d theta would be how far across you are. So that would be the part on the xy plane. Extend that up to the delta z, and there you've got your cylindrical coordinates. R, dr, d theta. Okay, r, dr, d theta, dz. dz is your 3rd dimension. Now, to convert those to back to rectangular equations, just like before, if this is your radius here, let's just take this point here, okay? Your r is how far from the origin you are. Your theta is how far you are from the positive x-axis, okay? And to get your x-coordinate, then that would be r times the cosine of theta, because this is your hypotenuse. Your x-coordinate would be over here, and that would be related by the cosine of the angle theta. Cosine is adjacent over hypotenuse. So that would be it's not particularly easy to see when they draw it 3-dimensionally this way. Your y, just like you had before, the y would be your, now there you don't really show. The y would be this perpendicular one here, yeah, 90 degrees. That looks a lot more than 90 degrees, but it's not. And then how far you're on the y scale, here's your theta here, so your y would be how far you are from the x-axis here, because that would be your measure of y, and that would be r times the sine of theta. So r times the sine of theta. And then the z is just the z. That's the same in rectangular coordinates as it is in cylindrical coordinates. How far you are from the xy plane. So these are how you go from cylindrical coordinates to Cartesian coordinates. Going the other way, just like before, x squared plus y squared equal r squared. That's how you get your r, how you get your theta is y over x is equal to sine over cosine, which is tangent theta, so it's the inverse tangent of y over x, okay? And z is equal to z. So in this coordinate system, simplest solid region is a cylindrical block determined by r's going from R1 to R2. That's these values here. Your theta is going from theta 1 to theta 2. That's that angle there. And z is going from z1 to z2. So that's your, they call it a cylindrical block. Sort of a weird name. It's not really a block. The r part is sort of blockish. The theta part, though, is sort of going outward. So it's more like a frustum type deal. And then your z part is like a block. Okay. To obtain the cylindrical coordinates form, to obtain the cylindrical point, I think that's supposed to be from, no, cylindrical coordinate form of a triple integral. That's what they mean, okay? Consider a solid region Q whose projection R onto the xy plane can be described in polar coordinates. That projection on the xy plane is going to be your polar coordinates. So the Q will be the set of all xyz triplets, xyz, such that xy is in R, and that projection R, h of 1, that some function down here is less than z, and z is less than h of 2, so z is somewhere in between those. And the R region down there is the set of all r theta, which is pretty interesting. Put this in xyz and put this in r theta. So theta is between theta 1 and theta 2, and your r is between some g1 and g2. Okay, and that's your region in R. All right. If f is a continuous function of the solid Q, then you can write the triple integral of f over Q as triple integral over the solid region Q of f of x, y, z, whatever that function is, okay? So a continuous function of the solid Q. Then this would be your rectangular region down here. It's not really a rectangle, but the region R that you're projecting onto is not a rectangle, okay? And the dz's, if you do that first, then this is just going from h of 1 of z, h1 of xy to h2 of xy. So you see both of these variables are here, so take care of that. These are your z variables, okay? Now, they still have everything in xy coordinates, so I don't know why. It seems like they would be in cylindrical coordinates, but they haven't put them there yet. So this is a function of x, y, z, dz, and it's going from function h1 to h2. And then you'll have the area of your region R, dA there. Where the double integral over R is evaluated in polar coordinates. Okay? This part is in polar coordinates. This part, the z is the same as it is in xy. That is, R is a plane region that is either R simple or theta simple. And if R is R simple, capital R is little r simple, then the iterated form of the triple integral in cylindrical form would be, your R would be the thing you do second, and then the theta the thing you do last. So what you do is change this to r theta. Your h1 and h2 now will be, because x is r cosine theta, y is r sine theta, you get these in cylindrical coordinates, and you're doing your dz first because it's going from h1 to h2. Your g of theta next, I'm sorry, dz first as it goes from h1 to h2. dr next as it goes from g of g1 of theta to g2 of theta. From here to there, okay? Those are your R values. And then finally your theta is last. And they say this is the R simple. I guess that's right. I would have thought theta simple, but it's R simple. Okay, and you go from spanning whatever your swath is of your theta there. Okay. Now, things to note here. Of course, your X is R cosine theta, your Y is R sine theta, and your Z is theta. But remember, polar coordinates, this is a length measurement, that's a length measurement, that's an angle measurement, so you need an R d theta. So really the R goes with d theta, but you can move it anywhere you want to, and you could move it just before you did the dr, you could move it here with dz, you can move it here in this one because you're doing the R here, any place that you wanted to do it. Of course, this is, you got R theta and Z, X, Y, and Z here, so you got all three of them in that. All right. I don't find this description particularly enlightening. It's all true, but it's just not very enlightening. So to visualize the particular order of integration, it helps to view the iterated integral in terms of three sweeping motions. Now, why they put motions capitalized, I don't know. Each adding another dimension to the solid. For instance, the order of dr, d theta, dz, if you're doing them that way, your R is going from some value to some value. Now that value will be determined as a function of theta and z, or not. So the first integration occurs in the R direction as a point sweeps out a ray. Then as theta increases, you do that one next as it sweeps out a sector. And then finally you do your sweeping up and down as z goes. In that case, the z will be the last thing, and it goes from z equals z1 to z2 or something like that. There won't be any dependence in it. This one, you could have your r's in this because you're doing your dr first, so you could be thetas and z's in the limits for r. You could have z's in the limit for theta, but you only have numbers in the limit for z. Okay? So, if this is what you're doing, covering this wedge here, which would be set up perfectly for cylindrical coordinates, to be used like cylindrical coordinates, you first integrate from along your dr, so you would do from 0 to r, or this could be some function of theta and z too, but it doesn't have to be. But if that's your first one, integrate with respect to r. And then sweep from theta equals 0, the way they show it here, to theta equal pi halves. This way, this is just simple integration. 0 to r, theta from 0 to pi halves, and then z from 0 to whatever your max z is. Now, if you do this one first, that r that goes with the d theta has to be factored, incorporated in this term. You can't have it dragging around to there because you have to make sure you get your r's done first, the way they've shown it here. So here's, find the volume of a solid region, Q, cut out of a sphere, which is x squared plus y squared plus z squared is equal to 4. So this is radius 2, and it's really not too clear that it goes to here, to there, back to there, and back to here. Now, even though you see it extending beyond that, that's just because it's blocking part of this. The sphere is blocking it, but it curves around and ends there, ends here. Again, it's not really clear. This is on the curve here, and this is as far out as it gets this way. But because of your perspective, you still see some sphere back there. So later we'll will say, why don't we use spherical coordinates? But cut out the sphere of x squared plus y squared plus z squared equal 4 by the cylinder r is equal to 2 sine theta. Okay? So your radius here, r is equal to 2 sine theta. All right? That basically is a when this is sort of hard to talk about. Here's one way to think of this. This is not particularly great, but one way to think of it. There's your region R, and that is a circle that's in there at the origin now, on the XY plane. Okay? Now it start moving up and down, moving in the shape of the sphere here. Now, this isn't particularly great, but you can say r squared is equal to 2r sine theta, right? R squared is x squared plus y squared, and this would be 2 times r sine theta is y, okay? So x squared plus y squared is equal to 2y. Now, again, this may not be the best way to think of it. Let me get my pen set up. I wasn't going to spend too much time on this, but this is a rather bizarre problem. X squared plus y squared is equal to 2y. That's what that turns into. So this would be x squared plus y squared minus 2y is equal to 0. Well, add 1 here and 1 here, and this gives you x squared plus y minus 1 squared is equal to 1. Okay? So what you have here is a circle, that's what the circle is here, whose have they drawn this right? Yeah, they have. The center of that circle is when x equals 0, which is on the y-axis, and the center in the y direction is that y is equal to 1. So you have a circle of radius 1 inside here, okay, that's on the xy plane, and then that same circle is going up. Now here, it actually, that comes together right there at the boundary of the sphere, and then the boundary of the sphere cuts it off here and here. Okay, rather a strange looking shape here. Okay, so find the volume of the solid region Q that's inside this purple area here, cut from the sphere radius 2 by the cylinder radius 1, centered at 0, 1. Radius 1, that's what this is, got. It's shown here. Okay, now, how are we going to proceed with that? Well, r is certainly a function of theta, so we want to do our r calculation near the beginning. And up here, we have, let's rewrite this one too, and this would be z squared plus r squared is equal to 4. So you have z squared is equal to 4 minus r squared. I can't write. I don't know why that's not writing well. Okay, so your z also depends on r, and then you could do this as, and you're doing a volume, so I would say z is equal to the square root of 4 minus r squared. Okay? Now, actually that should be plus or minus, but if you go your integral, when you're doing the dz's, you'll go from 0 to 2 and double it, okay? Not that you would end there, okay? So, you've got z as a function of r. Here we have r as a function of theta. So it looks like to me that we probably integrate with respect to theta first, and no, not first, because that's possibly, yeah, z going from square root of 4 minus 0 to square root of 4 minus r squared. That's going to be an early one, and then do your r next, and that goes from 2 to theta. And then, where are your theta going from? That's a little bit tougher to see. Probably 0 to pi. That looks like where that would be going. So let's see how they do it. Because x squared plus y squared plus z squared is equal to r squared plus z squared. That's equal to 4. The bounds on z would be from minus root 4 square root of 4 minus r squared to positive root 4 square root of 4 minus r squared. Frankly, for me, do twice 0 to square root of 4 minus r squared. So that's going to be one of the early integrations. Let r be a circular projection onto of the solid onto the r theta plane. Okay? Then the bounds for r would be 0 to is less than r is less than 2, which is true. And theta will be going from 0 to pi, which we said before too. Okay? So I think the first integration let's see how they set it up. Now, here's where I would differ from it. I would do 0 to square root of 4 minus r squared and put a 2 out front, because everything's the same above and below the xy plane. So do that one first, and this is doing your dz's first, because the z is between those two. So that's you do first. Then you do your thetas, and that's from your r is going from 0 to 2 r sine theta. If you recall back when I first said that, yeah, r is 2 sine theta, so that's your r dependency there. So it's going from 0 to 2 sine theta. So that would be the second integration you would do. And so I would do 2 out here, 0 to 4 minus r squared, r dz theta. Do the dz first, because that's between those two. Then your r is going from 0 to 2 sine theta. That would be your next one. And then the final one will be your theta is going from 0 to pi. So there's the formula for your volume. Remember, it's always r with d theta, but you can move it anywhere you want to. In fact, it's always good to lead with the r and have the d's at the end there. Okay. But because you're doing the dr second, that the r could be moved inside here. That's the dz here, twice between 0 and that. Then you got r in your this part too with that r, And then once you integrate that with respect to r, then from 0 to 2 sine theta, because that was what you were given originally, and then 0 to pi on your d theta. So that's why the d theta is the last. All right. Okay, now they did one more. They did 0 to pi halves and then double that. And that certainly works too. But if they did that, why don't they do the symmetry here too? So I have 4 here, have this 0 to the square root of 4 minus r squared. This is 0 to 2 sine theta, and this is twice 0 to pi halves. Okay. The first integration then would give you that, and you see you wind up with the same thing you would have had if you had done the 2 out front and then had r times square root of 4 minus r squared. Now, the reason they didn't, and this is not intuitively obvious, it works out well because you want the derivative. If you have this being your u, and then du would be minus 2r dr. So you see that fits perfectly, except you have a minus in that. Okay? And then you can do a substitution. Let's see if they show that. They skip a few steps, but that's pretty much what you've got. The minus sign that I was talking about, they now have it here. I see no reason not to bring this out here. Have minus 4/3 here, and then 4 minus r squared to the 3/2 power. But you evaluate that when you r is going from 0 to 2 sine theta, so you'll get sine thetas in there, and that there they show the 4/3. Now, when you're integrating with respect to r, they sure don't show they skip an awful lot of steps here. See where the 4/3 come from when you pull that out. They drop the minus sign because when they do the next integration, that's with dr, what happens is when you evaluate here, this is your r value, 4 minus 4 sine theta squared. That would be cosine, 4 times cosine theta squared, cosine squared theta. And then when you do integrate that, you would wind up with, well, you've already integrated, but when you plug those things in, you come up with a negative again, and then the negative here, and the other negative you get when you plug in will wipe out, and then you just go here. Now, it's not really clear where the 8 comes from here. It looks like they left the 2 in there, the 4 in there, but it looks like they pulled the 4 out. But so sort of hard to see. No, this 4 came from this. This came from that. Okay, when you squared that. Okay, and then when you integrate that one, that is a really pretty hairy integral. The 8 d theta, that just comes out 8 theta, and you evaluate between 0 and 2 pi. But this one you have to do, basically go to a table. If you remember how to do that, you can, but they say factor out and use the trigonometric identity that cosine squared is 1 minus sine squared. So, so they factored out the 8, and that got you to 32/3. And so that's gone, so you have a 1 minus cosine theta, one of those. The other two give you this. So is that the 1 d theta, that's just theta. So that's taken care of. This will then be minus a cosine theta d theta. You can do that. That's going to be a sine. Okay? And then minus a minus gives you a plus cosine theta sine squared theta. Well, that's going to be u squared du. So leave a sign or something in there. SIG and sign change. So that's what you get. A theta, a sine theta, and then a sine cube theta over 3. Okay, plug in your 0 to 2, and that gives you 16/3. Now, it's not really obvious where that comes from. Times 3 pi minus sine of pi at pi halves would be 1, so it would be a minus 1 there. And sinus pi, I'm sorry, I can't talk. Sine cube at pi halves would still be 1/3, so you have a minus 1/3. So that's where the 9 comes from. And not so super clear, but that's what you get. When you plug in theta going from pi halves, this becomes a pi halves, and bring in whatever you need to. And I think they have to evaluate it there. And they just skipped a bunch of steps. Let me just put it that way. But sure enough, you get, I'll take their word for it, that's what you get as a final answer. Skipping lots of steps, which is something in the neighborhood of 9.644. Let's see if that makes sense. This is close to 9. 9 minus 4 is 5. 5 times 16 would be close to 80. 9 will go into 80. Yeah, this is a little bit more than 80. So yeah, that does look a reasonably close answer. 9.644. Okay, now let's look at triple integrals in spherical coordinates. How are we doing on time? These are a little different because now you're picturing a sphere or some sort of a spherical type shape. The rectangular conversions for spherical coordinates are, and these are strictly solids. You don't deal with this in two-dimensional at all. And here's part of the reason why. Notice we don't have any r's in here, we have a rho. Rho is the radius of the sphere, not the radius of in the plane. Okay? Now, if this is your angle, okay, let me get these down. So the rho is sort of like your r, not quite, sort of like it. Your theta is very much like your theta was before, going from 0 to pi half, say, from here. So this is your d theta this way. Your phi, however, is the distance, is the angle seems like they would show a better picture than this. Okay. Boy, they do a lousy job of showing this. Maybe on the next slide it'll show it better. But your phi, your z is rho times the sine of phi. That basically is the best place to start. The if this is your rho, that's your radius of the sphere. Okay, so a delta rho sub I with how much it changes from here to here. There's your inner radius, outer radius. So there's your delta rho sub I. Okay, your phi is the angle from, I believe it's from here. You would be tempted to say phi from down here, but I believe they do the phi from vertical. Okay? And then the sine of phi, if this is phi here, the sine will be, nope, wrong. Phi would be your, from the here up, because your sine of phi would then be the distance z, between here, because that would be from your base to here. So that is your z is rho times the sine of phi. Now, your y has the sine phi and cosine theta. Now, theta is measured this way, so your x is going to be have a cosine theta involved with it, and there that is. Your y will have the sine theta involved with that, but both of them will have the phi times the sine of phi, rho times the sine of phi. And by the way, that is phi or phi. Some people will call it phi, but it's usually pronounced phi. It looks a lot like my zeros because I slashed my zeros, but that's no longer zeros. Those are angles phi. And see, the rho sine phi is the height basically you have here, and then do the sine of theta connected with that, and that's what gets you up here. Your x is this way, your y is this way, and your z is that way. So they all have something to do with the rho sine phi. Okay, in that coordinate system, the simplest region is a spherical block determined by a set of all values rho sine theta, such that rho is between rho 1 and rho 2. Rho 1 and rho 2. Theta is between theta 1 and theta 2, so there's your, that one. And phi is between phi 1 and phi 2. Here would be your phi 1, there would be your phi 2. Taken from the base up. Okay. Now, the incremental volume of this thing would be your rho, or your delta rho. Here, that would be your link this way. Your rho sine phi, cosine phi would be your amount in the x direction. Rho sine phi sine theta would be your amount in the other. So you have a rho squared sine phi and they've sort of lost the thetas in there all completely. They just have the delta theta. Delta theta rho would be this dimension, delta theta phi would be that dimension, and your rho would be, delta rho would be at that dimension. So you see your length dimensions come from the rho, and the delta rho. The others are just angle measures. Okay, that's sort of a simplistic way of looking at it. So if the rho, theta, phi is a point on the interior of such a block, then the volume of the block can be approximated by just that little block, delta v, be rho squared, sine phi, delta theta, delta phi, delta theta. Okay. Delta rho is that length. Rho delta theta would be associated with your z, and rho delta theta, rho delta phi is associated with the z, rho delta theta, your x's and y's to some extent. Using the usual process of involving an inner partition, summation, and limit, you can develop a triple integral in the spherical coordinates for a continuous function F defined on the solid region R. If you're integrating this thing over the whole volume, then, and again, the order doesn't matter too much, but since you got rows in here, you got rho sine phi, rho cosine phi, rho sine phi, cosine theta, rho sine phi, sine theta, and rho cosine phi. So you got rows in all three of those. You got a rho square here and a d rho. Yeah, go on and do that one first. Integrate those out. If it's helpful, if it seems like it's doable. If it's not, try another one first. Your d phis, you have a phi here, 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 and here. So yeah, deal with the phis next. And then finally, your d theta, you only have thetas here, here, and not even there. So d theta is not a bad thing to do last, unless it's more helpful to do it earlier. Okay. Triple integrals and spherical coordinates are evaluated as iterated integrals. You can visualize a particular order of integration by viewing the iterated integral in terms of three sweeping motions. Again, the capitalized motions, I don't know why, each adding another dimension to the solid. So let's see what they mean here. Okay? Now they're doing the d rhos first, then the d thetas, and then the phis, and then the d thetas. So the d rho would be going out the radius, okay? Wherever that radius happens to be, the show it in the center, but it can be anywhere, okay? And rho varies from 0 to 3. Now, this must be a special problem. They don't tell you what it is, but it must be somewhere in, oh, here it is. Rho is equal to 3, okay? Rho varies from 0 to 3. Your sphere then would be going x squared plus y squared plus z squared is equal to 9. The cone here, as your angle, phi varies from 0 to pi fourths, so it's going up here. No, they showed phi this way. That's what I thought. Phi was always this way. And so going from 0 to pi fourths, and then your theta is going all the way around 0 to 2 pi. So your rho is going from 0 to 3 out any radius, okay? Phi is varying from 0 to pi fourths, coming down this way, and then your theta going all the way around. Find the volume of this is the example for a solid region bounded below by the upper nap. I've never seen that one before, of a cone. Z squared is equal to x squared plus y squared, and above, below by the upper nap of the cone. So I guess that would be the surface in here, I guess is what they're calling the nap. That's what's on the bottom side. Z squared is equal to x squared plus y squared, and above by the sphere, which is radius 3. Okay? X squared plus y squared equals 9 squared. Okay? Frankly, I can't see where the wrong. Okay. If your cone's sitting in here and you have a sphere that you're cutting with it, then the cone portion, the cone is flat here, okay? And so what you're doing is from the upper part of that cone to here. So you're going from This is 0 to 45, is what I think I remember seeing here. Volume. And so it's the part that the cone would cut with the sphere, the portion of the sphere that's above that. Okay? So your rho is going from, if this is 45, I don't know where I got that, but it seemed like that's what cone is z squared plus equal x squared plus y squared. And the sphere is that shown here. Okay. See how they do that. Spherical coordinates, the equation of the sphere is rho is equal to, rho squared is this, so rho is going up to 3. Now, it doesn't show where it starts, but it goes up to 3. Rho is equal to 3. That would be the way you express that in polar coordinates. I mean, cylindrical coordinates. Spherical coordinates. Furthermore, the sphere and the cone intersect when x squared plus y squared. And let's go back to this. X squared plus y squared is equal to z squared. So if you have this, that would be z squared plus z squared equal to 9. So that would be, is that how they do it? Yeah, z squared plus z squared is equal to 9. So that would be 2z squared is equal to 9. Divide by 2, and then take the square root of z, and you get 3 over root 2. So that's where your z is. That's the lower z going up to 3. Okay? Because z is equal to rho cosine phi, it follows, I knew this, I figured that was what it's going to be. Follows that 3 over root 2, that's your z. Okay. So the z, which is root 3 over 2, yeah, is equal to 3 times cosine phi, okay? And so divided by 3, so cosine phi is this, and that would be 1 over root 2, so your phi would have to be 5/4. I thought that was in there somehow, okay? Consequently, you can use the integration order d rho is going from 0 to 3. I wouldn't have thought it would be 0 to 3 with this, okay? Your phi is going from 0 to 5/4, and theta is going all the way around. Now, let me back up here and see if I can figure out. Maybe they talked about the entire volume of this cone, which has a scoop of ice cream on top. Not just the cone, but that. So then your rho would be going 0 to 3. I thought they were just doing the green part here, but they must be completely filling the cone up to there. So that's what they mean by the nap, I guess, of the cone up to the surface of the sphere. So I had misinterpreted that. Sorry. So your rho is going from 0 to 3. The phi is going from 0 to 5/4, and then theta 0 to 2 pi. So, doing the rhos first, and see, all these are just pure numbers, so you don't have to have any variables in here. And your volume element is rho squared sine phi d rho d theta d phi d theta. Okay? Doing the rho first, 0 to 3. Sine phi just gets carried through that. This becomes rho cubed over 3. When you integrate that times sine of phi, do the phi's next, And that way you integrate that, and that gives you a minus cosine phi from 0 to pi fourths. And find thetas. You don't have any thetas anywhere in there, so it's just 2 pi would be what you get from that. Okay, so that would be the first integral would be, this one would be rho cubed over 3, going from 0 to 3. And rho cubed at 3 would be 27 divided by 3 would be 9, so that's where this comes from. Sine phi just gets carried, then you do your d phi. Okay, I would go on and take the 9 completely out, okay? And then the integral of d, sine phi d phi, antiderivative of that would be a minus cosine. That would be 0 to pi fourths. And at 0 it's 1, and at pi fourths it's root 2 over 2. So this is going to turn out being a negative, and that will cancel out the negative here. So you'll be that. So this would be root 2 over 2 minus 1. So that would be positive 1 minus root 2 over 2 without the minus sign in it. And so there you have your 1, 9 on the outside, 1 minus this. And you can take this on the outside and then just get a 2 pi in here. So you'd have 9 pi, if you did 2 pi times this, if you make this 2 minus root 2 over 2, then the 2 from the 2 pi will cancel that out. You have a 9 pi, and the 2 will cancel that out, 2 minus root 2. Now, this is approximately 27. This is something about 0.6. 27 times 0.6. I don't know. 15, 16, somewhere around in there. 16.563. Okay. So that's how you do spherical coordinates. And that is the end of the slideshow. All right. Except for saying that there's a German mathematician named Carl Gustav Jacobi. He is known for many areas of mathematics. His interest stemmed from finding the circumference of an ellipse. Interesting thing. But anyway, the feature called the Jacobian was named after him. And since we really don't have time to get into this very deeply, I'd say, what do you think? Let's just can it there. And hopefully you won't need Jacobians in your work, but if you do, they're a pretty simple definition. You want me to just flash it up there so you'll see it? Okay. So let's just get out of that. And so let me just show you what a Jacobian is. Sorry we didn't get to chapter 15. That was some pretty good stuff. Hopefully you won't miss it too badly, but if you do, go to larsoncalculus.com and you can follow a lot of it there. Okay, so let's go slideshow, current slide. Okay. Here is your definition of a Jacobian. If x is some function of g of u of v, y is some other function of u of v, h of u of v, then the Jacobian of x and y with respect to u and v is denoted this way. The partial of whatever function you have here that's a function of x and y divided by the partial, or with respect to the partial in u and v, would be, now this is your determinant sign, okay? Partial of u with respect, x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v down here, and then your Jacobian is the determinant of that, which is partial of x with respect to u times the partial of y with respect to v, minus, that's what a determinant does. Your down diagonal was positive, the product is positive, the up diagonal, the product is negative, minus partial of y with respect to u, partial of x with respect to v. Okay? So that's what your Jacobian is. That's your definition. And that somewhat enables you to convert from UV to XYs or vice versa. So that's just what a Jacobian is, and you can go on with the rest of it. We won't go any further than that. Okay. Good deal. Any questions? All right. If you haven't already turned in the last test, please do so within the next few days. Okay? You've got till Friday to do it, but I would say please try to get it in. If possible by Wednesday, if not possible. Did everybody get a copy of the third test? Okay. I tried to email it to some of the people who weren't usually here. I think at least one of us brought that in. So anyway, if you can get it in by Wednesday, great. Remember, I'll be here on this campus Wednesday from 8 to 12:30, and I'll be over on the Birmingham West campus until 6. But you can slide it under my door if you finish it sometime then. Otherwise, I'll be here Thursday from 8 to 4, and then back on the Birmingham campus. But that's the last moment I'll be here on this campus. It's 8 to 4. So please try to, if you're going to turn it into this campus, get it to me before Thursday at 4. If you can take it to the Birmingham West campus and B122 after 4 o'clock on Wednesday, you can take it after 4 o'clock on Wednesday to East Campus, the Ethel Hall building, room 214 in the Ethel Hall building, the nursing building. You can take me to me there between 5 and 6:30, or during office hours. Don't slide it under a door anywhere over there because they don't know what to do with it. But during office hours, if you don't catch me, give it to the secretary in B122. That's Miss Rose Saxton. She'll give it to me when I come in. I'll be there 8 to 12. Usually I'm there before her on Friday, so 8 to 12 on Friday. She may or may not be there first, but I'll be around 8 to 12 on Friday. After that, it's going to be an incomplete because I'm planning not to be here on Monday at all. Okay? So get it to me when you can. Good deal. I've enjoyed having you in class. Have you done student course evaluation yet? You have? Good. If not, please do those. Don't forget to do those. All right.